A single blade can stretch longer than a football field, yet it's built by hand, layer by layer, like a giant sheet of paper mache. A steel tower can weigh more than 300 elephants, yet it's designed to sway on purpose. Inside a housing the size of a school bus sits a gearbox spinning fast enough to shred a car, yet it runs for 20 years without stopping. And the whole structure is raised hundreds of feet in the air, using a crane that costs more than the house you live in. That shouldn't be possible. So how do engineers turn steel, resin, and fiberglass into machines that can power thousands of homes from nothing but moving air? Let's step inside and find out. A wind turbine blade doesn't look like it should bend, but it has to. Every single one is engineered to flex several feet in strong wind without snapping, cracking, or losing shape. It's one of the largest man-made objects that's still designed to move. It starts as nothing more than rolls of fiberglass fabric, stacked sheet by sheet inside a mold that's longer than a bowling alley. Alongside it sits a tank of liquid resin and a core of balsa wood or foam that will become the blade's internal skeleton. Some manufacturers even use recycled wood fiber in that core, shaping it into a honeycomb pattern that adds strength without adding much weight. Workers lay the fiberglass sheets into the mold by hand, angling each layer in a slightly different direction, a technique borrowed from how plywood gets its strength. Dozens of layers go in before the mold is even half full, each one smoothed down to remove air pockets that could weaken the structure later. Once the layers are stacked, the mold is sealed shut and connected to a vacuum system. Air is pulled out completely, and liquid resin is drawn through the fabric, soaking every layer evenly in a process called vacuum infusion. Engineers watch the resin flow in real time because if it moves too slowly through even one section, that spot ends up dry and structurally weak. The entire mold is then heated to around 70 degrees Celsius, curing the resin into a single solid shell over several hours. Two halves, an upper and lower shell, are bonded together with adhesive thick enough to fill a bathtub, then sanded, inspected, and painted with a lightning conductive coating running the length of the blade, since a blade this tall is essentially a lightning rod every time a storm rolls through. A single misaligned layer of fiberglass, just millimeters out of place, can create a weak point that fails years later, thousands of feet in the air, under hurricane force stress. So every layer is checked twice by hand, and some factories now use ultrasound scanning to look inside the finished blade for flaws no eye could catch from the outside. What started as flat rolls of fabric is now an 80-meter blade, curved, tapered, and balanced to spin at speeds that would tear a smaller structure apart. It gets weighed, measured, and matched with two other blades of nearly identical weight, because even a small imbalance between blades can shake an entire turbine apart over time. Before it ever leaves the factory, the blade is mounted on a test rig and flexed thousands of times in a row, simulating years of wind stress in just a few weeks, to make sure it can handle decades of real-world punishment before it's trusted 100 meters in the air. While the blades are curing somewhere else in the factory, the turbine's spine is already taking shape. The tower looks like a simple steel tube. It isn't. Every tower is engineered to sway, because a tower that refuses to move is a tower that eventually breaks. It begins as massive flat sheets of steel plate, some over 30 millimeters thick, delivered on flatbed trucks straight from a steel mill. Each sheet is inspected for surface defects before it's even allowed onto the factory floor, since a single hidden flaw in the raw steel can compromise the entire section built from it. The steel plates are fed into a rolling machine that curls them into cylindrical sections, section by section, until each forms a tube roughly the width of a school bus. The seams are welded shut using automated welding arms that move at a precisely controlled speed. Too fast and the weld is weak. Too slow and the steel warps from the heat. Each finished section, called a can, is tested with ultrasound and X-ray to check for hidden cracks inside the weld that no human eye could catch. The cans are then stacked and bolted together, anywhere from 3 to 5 sections, using flange rings bolted with over 100 bolts, each torqued to an exact specification with a calibrated hydraulic wrench. Because an unevenly tightened bolt can create a stress point that fails years down the line. Finally, the entire tower is sandblasted to bare metal and coated in multiple layers of anti-corrosion paint designed to survive decades of rain, salt air, and constant UV exposure without peeling or rusting through. Engineers actually design towers to flex up to a meter at the top in strong wind. A perfectly rigid tower would fight the wind instead of absorbing it. And metal that never bends is metal that eventually fatigues and cracks under repeated stress, the same way bending a paperclip back and forth eventually snaps it. What was once flat steel sheet is now a tower capable of standing over 100 meters tall, engineered not to resist the wind, but to work with it section by bolted section. The blades are curing, the tower is coated and ready. Now comes the part that actually turns moving air into electricity. Inside the housing, sitting at the top of every turbine, is a spinning shaft that can hit speeds of over 1,000 revolutions per minute, from wind that, at ground level, would barely ruffle your hair. The nacelle starts as a steel frame, essentially the turbine's chassis, onto which every mechanical component will be mounted piece by piece on the factory floor, much like a car chassis before the engine and body panels go on. First comes the main shaft, a solid steel rod connected directly to the blades, spinning at a slow 10 to 20 revolutions per minute. That's far too slow to generate electricity efficiently, so the shaft feeds into a gearbox, a set of precision-cut gears that steps the rotation speed up dramatically, sometimes by a factor of 100. From there, the fast-spinning shaft connects to the generator, where spinning magnets pass by coils of copper wire, inducing an electric current strong enough to feed directly into the power grid. Sensors and a yaw motor are installed to constantly rotate the entire nacelle, keeping the blades facing directly into shifting wind, adjusting automatically dozens of times a day without anyone touching a single control. Every wire, bolt, and bearing is tested on the factory floor. Before the housing, a fiberglass shell built almost the same way as the blades is lowered over the top like a lid, sealing the delicate electronics away from rain, dust, and salt air. That gearbox has to survive constant, unpredictable torque from gusting wind for 20+ years without being open for major repair. Which is why some of the largest turbine gearboxes cost more than a luxury car just for that one component, and why technicians monitor its internal temperature and vibration remotely, around the clock, from control rooms hundreds of miles away. What began as a bare steel frame is now a fully sealed power station in the sky, ready to convert wind into electricity the moment it's connected to the grid. Every piece now exists on its own: the blades, the tower, the nacelle. But none of it generates a single watt of power until it's standing hundreds of feet in the air. Raising a wind turbine isn't like raising a building. Every piece has to be lifted, aligned, and bolted together hundreds of feet above the ground, often in wind speeds that would ground most cranes. It starts with a concrete foundation, sometimes reinforced with enough steel rebar to fill a warehouse, poured weeks in advance and left to cure until it can bear hundreds of tons of load without shifting even a fraction of an inch. A crawler crane, one of the largest mobile cranes on Earth, arrives on site in pieces on dozens of trucks and takes days just to assemble before it can lift anything at all. The tower sections are lifted first, stacked and bolted one on top of the other, each one checked for level before the next goes on. Once the tower stands complete, the nacelle is hoisted to the top and secured onto the yaw system. Then, one by one, each blade is lifted into place and bolted onto the hub, a process so precise that crews often wait for a narrow window of calm weather, sometimes just a few hours long, before attempting the lift. Finally, technicians connect the electrical systems, run diagnostics on every sensor, and slowly rotate the blades for the first time to confirm everything moves exactly as designed. A single gust at the wrong moment during a blade lift can swing an 80-meter piece of fiberglass like a wrecking ball, which is why some installations are delayed for weeks, simply waiting for the wind to cooperate in what might be the only construction job on Earth that gets halted by the very thing it's built to capture. What started as separate pieces of steel, fiberglass, and copper is now a single machine, turning slowly, converting the same wind that once delayed its own construction into electricity that will flow into homes it will never see. From here, The turbine will run largely untouched for the next 2 decades, monitored remotely, serviced occasionally by technicians who ride an internal elevator up the very tower that took a crane and a crew of dozens to raise in the first place. That's how a wind turbine goes from flat steel sheets, rolled fiberglass, and raw copper wire to a machine capable of powering thousands of homes for the next 20 years, quietly, without a single drop of fuel burned. Precision, patience, and engineering most of us never think about, until now.